In this demo, a model will be initialized in Ruby from a geomodeler, where a large dataset in Eclipse GRDECL format will be loaded directly. We will also simplify the grid by reducing the number of layers. Let us create a new Ruby document. Then, define the reservoir boundary from an ASCII file containing the nodes in a simple XY format. Next, we load the GRDECL or CMG format file containing the layer horizons and petrophysical properties. We observe that the file contains a large number of layers, 62 in total. The user is also asked to confirm the length unit used in the target file and choose which properties to load. It is advisable to reduce the number of layers, as loading a fine geological representation may not be adapted nor required by the Ruby simulation. Based on a permeability average difference criterion between two connected layers, some layers can be merged if they are below this threshold. This interface allows you to enter this threshold and also set a maximum number of layers. Let us simplify the layers to 10. We will proceed to visualize the layers. We can also edit any of the points loaded by clicking on the property map. In a similar fashion, we can edit the petrophysical properties of each layer of the simplified grid. For instance, let us display the net to gross map for layer 2. Similarly, we can display the permeability and porosity maps for each of the layers. Note that we will still need to define the PVT and wells in Ruby, as these are not transferred from the GRDECL file. Now, let us create two vertical cross-sections across the reservoir. Then, we proceed to the simulation page to construct the grid. Here, we display the porosity distribution across the vertical cross-section 1. And also display the permeability distribution across the vertical cross-section 2. We can also view the net to gross distribution in the 3D geometry plot. Now, let us open a Ruby file in which the same GRDECL grid has been loaded with various simplification levels for the layers. Here we have created three cases, one with a 5-layer simplification, another with 10 layers, and a third with the original number of layers without any simplification. These three runs are created from the same GRDECL input file. We have placed a vertical well in the middle of the reservoir and then run a simulation so as to validate the vertical upscaling of the layers used in the two runs. The well is being produced at a constant bottom hole pressure of 3000 psi for a 1-year duration. We can view the simulated gauges and the 3D geometry plot. Let us compare the simulated bottom hole rates from the 3 runs. This shows that the simulation results are consistent in all the 3 runs, with a less than 2% difference between the run with a 5-layer simplification and the run without any simplification. We can also compare the number of grid cells and relative CPU times. The 5-layer run required about 3000 grid cells, whereas the 62-layer run required about 38,000 grid cells, which is 12 times more number of cells. Comparing the relative CPU time spent in the simulation, the run with 62 layers took about 23 times more than the 5-layer case. This ends this session. To learn more, please feel free to download the Kappa DDA book. There are also numerous worked examples and datasets on the download page. Or, for more information, contact support@kappaeng.com or your local Kappa office.